Margaritifera in Austria, and it's a critically endangered species. So it has quite a complex life cycle. It needs, on the one hand, unclogged conditions in the substrate for the oxygen and the nutrient supply in the early stages of the life cycles. And at the same time, it needs to be stable enough that during flood events, the drifting is prevented. And it has to be also good conditions for the brown trout, because they live there in the first year in the gills. So you need, on the one hand, habitats for the fish and also for the mussel, and that's quite complicated in our regulated river systems like we have in Austria. So this is a picture from a stretch in Upper Austria, and we have this historical river geometry. And for flood protection, we see often these river widening concepts. It's quite a good idea to increase the discharge capacity of these river systems, but this system gets, after 5 to 10 years, filled up with sediments. Yeah? And during these 5 to 10 years, the sediment degradations not only happens on the left side of the river and the right side, it happens everywhere. So the substrate gets clogged and the mussel died. And this is more or less a lose-lose situation, because then you have the discharge capacity for flood protection and the ecology can't live there. So this is not the best idea to do this in these rivers. And then we see some interesting aspects, because the river defines its regime equation, or regime width. So this more or less quasi-stable river with building itself from the river. And so the basic idea is, how can we build or get this river morphology that delivers both, so the flood protection and also the ecology aspects. And we see these multiple stressors on river ecology systems, like altered morphology, increased sediment input due to the land use, and some climate change aspects. And we have only few natural river stretches left, so we do not really know what the perfect habitat of the freshwater pearl mussel looks like. So then we have only there is a lack of concepts to prevent these increasing siltations, and this concept is a basic idea how to build a river to deliver both, so the river ecology and the flood protection. We are in Austria. It's a country in so in Central Europe, and in Upper Austria, this is here in this area, there are the only conditions where the mussel can live. It looks like that. So it has nice hills, altitudes up to 1,000 meters, but the most cases of the rivers are between 600 and 800 meters. And the geology is, we have this granite and gneiss geology producing a specific sediment composition that I will explain a little bit later. Our materials and methods. So we selected 11 river stretches. So that's not the big amount, but these are the only ones that are suitable for these investigations. And we selected semi-natural stretches without bank stabilizations, and we used artificial near widening section where we can see these sediment degradations. We measured the river bathymetry, and we used the DM for the floodplain informations. Then we had to find some validation data set. Yeah, that's not it's really complicated because there are so few stretches left that are naturally. So we used just the basic information from the LiDAR data and the aerial photos and measured the river width in 17 river stretches. We measured the discharge in the cross sections for the calculation of our models, and we got the characteristic discharges from the Hydrographic Service of Austria. For the sediment composition, we took 102 samples along the profiles, always on the left side and on the right side of the river. surface and surface samples. We calculated in the first step the typical hydraulic parameters like river width and river depth, and therefore we used the software packages ArcGIS, AutoCAD, and HECRAS. And this is one example. So we see here this cross-section, this trapezoidal shape, the sediment aggradation, and the characteristic discharges, mean flow, 1 year flood, okay, bigger ones. Then we had a look on the sediment transport, so the start of motion especially, and we tested well-known regime equations. So there are a lot of investigations in that case, and it looks quite all the same. So you have an input parameter, this would be the x, and this is more or less the discharge, and you get the river width or the river depth, in some cases also the hydraulic radius. And you find these coefficients A and B in the literature for these equations. So the question is, there are a lot of equations, are they suitable for our case? And so we tested it for a 1 year flood, and we calculated the river width, so the prediction of the rivers, with these equations. And each column is the range of the results. And if you compare it to the modeled river width, then the black line would be the perfect fit between prediction and modeled river width. And you see, in some cases they are quite good, but in the most of the cases they underestimate the river width. So we think that they are not suitable for this catchment. So why do they not fit? We think it's more or less a grain size distribution and the specific sediment composition. We have on the one hand really fine material, 1 to 10 millimeters, and really coarse materials. So this is a B-model grain size fractions, and they are quite specific and typical for this catchment. And if you have a look on the sediment transport, especially in the start of motion over a year, you can see that most sediment transported between March and May, and between September, October, November, there's the lowest transport capacity. There are also stretches where sediment transport occurs every day, but in most of the cases, they are just transported over some days. So this B-model grain size characteristic is coupled of grain size about 60 millimeters, and these really fine materials are quite specific. And if we have a look on the minimum transport capacity of a year, we see that up to 40% the transport capacity the sediment is transported in years with low discharges, and in years with high discharge, the sediment is transported up to 60%. So the material is transported over the whole year, yeah? And that's also a big issue for this, for the ecology, because the material clogs always the substrate. So what happens if you compare the river width and the discharge? Then you can see for the mean flow that there is a correlation between this. And this equation is quite different to that published one. There is also a correlation between the river depth and the mean flow, and also the hydraulic radius. And we think for this sediment composition, the mean flow is the main driver for this river width. So the big question is, how can we validate this data? So we tried to compare this with this measured river width from the airborne LiDAR data and also from the aerial photos, and predict the river width with our equation for the mean flow. And we can see that it fits quite well for river width up to 7-10 meters, and then it doesn't work that good at all, yeah, for the bigger ones. But what is, if we say, okay, it's not the mean flow, maybe it's the low flow, then we get also an equation, and this would look like that. And then we would overestimate the river width. And if we do the same, like the published one equations with the 1 year flood or the bank fluid discharge, then we would also underestimate the river width. So these rivers build during mean flow conditions a specific river width. And this is more or less the equation we can use for for the channel design. Yeah, that's fine. So we know this just a limited data set. So 11 river stretches are not that big at all, but they're the only ones we have. The known regime equations mostly derived from gravel bed rivers, from gravel bed rivers, or for really large sandbed rivers. And the sediment compositions are quite different to ours because we have our mean flow is between 3 cubics up to 10 cubics, and that's really small rivers. And so also the input parameter, like the discharge based on the recurrence interval, like flood events 1 year up to 10 years, or the being for discharge is quite different to our system. So we think our result could be a suitable tool for river restoration in the first step. So you can go to plan your river restoration concept and doing afterwards the hydrodynamic models in 2D, 3D, have a deeper look into the sediment transport capacities. Yeah? But in the first step, it's maybe a good idea to have an idea how the channel could look like. So the summary and outlook. We have high amount of dominating grain size between 1 and 2 millimeters. They are transported during the whole year and causing these ecological problems. These B-model grain size characteristics could be one reason for the self-forming quasi-stable river width. And the redimensioning of mean flow channels could be a really nice tool for the river restoration concepts. And this is also a good concept for the local authorities to prove what the civil engineers are planning. So we try to investigate further river stretches. Maybe we go to the hydro lab to do some physical laboratory experiments, but maybe we can present this at the next conference. So thank you for it.